Hi, it's time for another math easy solution. Turn discuss further into calculus with parametric curves, and now go over surface area and go over part one of the derivation for the formula in parametric form. So recall from my earlier video that the surface area of a shape formed by rotating a function about the x-axis is given by the formula here. If f is positive and has a continuous derivative, we define the surface area of the surface obtained by rotating the curve y equals f of x. I'm using capital F of x because I'll use lowercase later in parametric form. And where x is between a and b about the x-axis. So if we rotated around this x-axis, we have a shape like this where this y equals f of x is positive. And this is the formula where s is equal to integral from a to b from here to here. 2 pi times y of square root or times square root 1 plus dy over dx squared, then dx like that. And this is the formula I derived in my earlier video, so make sure to watch that. And basically the surface area S is if we were to rotate this curve around the x-axis, we get a shape that looks something like this. And then we get, that's a bit high, it's right over here. So this is, I'm just going to mirror this over here. We get a shape like this, it's a mirror image, and then rotate all the way across like that. I'll draw this more circular. And then, yeah, so we get a shape like this when we rotate this all the way through, like that. And then the surface area is just all around the surface, like this. So this surface area is our S, and that's this formula across there. And now let's start deriving this formula, but for parametric form. And this is the same methodology I did for arc length, so make sure to watch those videos. I'll put those also in the video description below. So if instead we have, if instead y equals f of x was written in parametric form, so that function written in parametric form, then we could use the substitution rule for definite integrals to obtain, and then I'll put the proof of the substitution rule in the description below. So if we were to write that in parametric form, what we end up having is, let's just work out the steps. So x is equal to f of t. So let's say x is equal to a function of t, a third parameter t, and then we have y is equal to g of t. So that's why I put the lowercase here, and let's say you could write this as y equals f of x, where t is between alpha to beta, and where these t's correspond to, well, if we were dealing with this function, this is where we would have it. This is at t equals to beta, is where we get this point here, and then at this point is when we have t is equal to alpha. So now we can basically try to change this formula by using the parameter t instead of the x. So we could just write this down again. So we have, just to show you here, s is equal to integral from a to b of 2 pi y square root 1 plus dy over dx squared dx. So now we want to use substitution rule and change everything here to make it in terms of t. So the first step is, well, at x is equal to a, that's from here to here, so these are the first things we want to change. What we have as well, this is when t is equal to alpha, and in other words we have x of alpha, because remember x is a function of x is a function of t, like that. So x of alpha, this just equals to f of alpha, this equals to a, etc. So we could write this a is equal to x of alpha, like that. And then at x is equal to b, so that's this parameter. Again, we have t is equal to beta. Same thing as writing x is a function. We plug in the parameter beta inside the x is function of t. And this is the same thing as writing x of beta is equal to f of beta. This equals to b, not beta, like that. So that's this one over here. That's just equal to x of, or I'll just put that inside, I'll move it across here, b is equal to x of beta, like that. And there, I just fixed that up like that. So now that we have this, the next thing, well, this one, y, that's just, we could just keep that there. Y is just g of t. We're not going to change it. Or, yeah, so the next one we want to change is this one. And the reason we're not going to change this y, well, it will show up in the last formula anyways, but we'll just change it anyways for now. So y is just equal to g of t, just for completeness sake. So y is equal to g of t, and then next one we want to change is this dx to get in forms of dt. What we can do is well, we know that x is equal to a function of t, f of t. The derivative of this is, well, dx over dt. Actually, I'll put that over here. So we get dx over dt equals to f prime of t. So now if we move this dt onto this side, what we end up having is basically dx is equal to f prime of t dt. And where f prime of t is just, well, this one is just over here. That's just dx over dt. Like that, put the better arrow. Like that. So this means that this equals to, put this all combined, dx is this equal to f prime of t is just dx over dt, and then multiplied by dt. And we could solve this just by, well, multiplying dx by dt over dt. And so now what we end up having is, well, derivative of x times by dt. And this right here, we could throw that in there. And this is useful because we can multiply this dx over dt inside the square root. And we'll show you how that works. And now the next one is this dy over dx. So this one, recall from my earlier video on tangents and parametric curves that I showed that the dy over dx formula is equal to dy over dt over dx over dt. And I'll put the proof in the description below, so check that out. And this is where the bottom part here is not equal to 0. Yeah, so we're not dividing by 0 like that. So what we have now is, well, we could throw this inside right here. So what we have, combine these all together, we get s is equal to the integral from alpha to beta. Now if 2 pi y is g of t, like that, and then we have a giant square root. And now we have this dy over dx is instead this over here. So you have 1 plus, and now we have a dy over dt squared over dx over dt squared, like that, because we are squaring it inside. And now we have this dx like that at the end, which is over here. So now we multiply by dx over dt times it by dt. Like that. And the reason this doing that like that is, notice there's a dx over dt at the bottom here that's squared. What I'm going to do now is I'm going to square this and then square root it, so we're not changing anything, because it would just cancel. But doing that so that I can multiply this inside. Now these square roots, these are just same powers, you can combine them, and then we'll have this multiplied inside here. So what we end up having is s is equal to, yeah, so now what we get is, we just write this down, alpha to beta, so integral from alpha to beta of 2 pi. I'm just going to write this g of t as y because it looks neater, and we'll include that in our final result. And then we have this square root, and now this dx over dt squared times by 1 because it's inside the square root now, it's the same power. What we have as well, just dx over dt squared. And then the next thing is, write this t better. And the next one here, this dx over dt squared, they cancel with this at the bottom, so what we're left with is just a dy over dt squared. So dy over dt squared like that, and then finally we have at the end dt. And there is our formula for surface area of a parametric curve like this. And now what I want to make a note is that this derivation is for the case where the parametric equations x equals f of t and y equals g of t can be written in the form y equals to capital F of x, or just a function of x, i.e. a one-to-one function. Recall my earlier videos, one-to-one function is when we can write it like this, so that for any one x value, like this, we have one y value across here. So we don't have multiple y values for any x. But in fact, this formula is still valid even if the parametric curve can't be written as y equals f(x), and this is what I'll cover in part 2. For example, if you had a function that looks something like, let's say something like this, for example, and you want to rotate it that, so y x like this. This one here, as you can see, at this point you have x, you have multiple values of y. So you have y1 and you have y2, for example, for one value of y. And the next video I'll show that it's still valid for this, even though you can't write this as y equals to a function of x. And then we could rotate this, and you'll get some pretty crazy curves. I don't know how this would look like. Let's see if you were to rotate it. It would look something pretty ridiculous, actually. Let's see how this would look like. Yeah. So you can get a kind of feel for it. It will look pretty ridiculous curve. I'm not sure how this will look like. Yeah, here I quickly just drew this in red and then made this dashed line just to show you. I just want to see how it looks like. And then if you were to find the surface area, it would look something like that. And yeah, the dashed line will represent the inside. That's like the inside shape, and then etc. So you get a pretty crazy shape like that. Unreal. And we would need a 3D grapher or some sort just to see it. But anyways, yeah, I just want to give you an idea of how it looks like, and also for later videos we'll do some crazy stuff with these parametric curves. And also I'll go over this in part 2, so stay tuned to show you that it's in fact valid for, even if you can't write it like that, so for functions like this, parametric curves like that. Anyways, that's all for today. If you learn, like, yeah, hopefully you enjoyed this pretty extensive proof video. That's not too extensive, but it was just pretty in-depth. Hopefully you enjoyed, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.